Hi, and welcome to our presentation on PIN, a method for enabling object localization in frozen vision language models. I am Michael, and this is joint work with Nimrod Barasani, Case Snake, and Yuki Asano. First, we analyze caption-based vision language models like Flamingo to assess the object localization capabilities. We use prompts such as provide a bounding box around the cat and localize the cat in the image to test those abilities. We tested GPT-4 vision, which, despite its undisclosed training details, is likely not trained solely on captions. However, it struggles to verbally localize the cat, although it does produce a somewhat decent bounding box. What does OpenFlamingo say? Provide a bounding box to determine the size of the room, or the cat is localized in the image. Fromage warns us that cats are not fond of being confined in small spaces. And lastly, Blip2 responds even worse by saying the cat's plant. None of the open source caption-based models provide meaningful localization information. This is unsurprising, as they were trained solely on caption data without instruction tuning. With our proposed method, PIN, we can adapt vision language models like OpenFlamingo to enable their object localization abilities. This allows us to leverage the extensive general knowledge within vision language models. Our method involves three key components: an off-the-shelf frozen vision language model, our PIN module, which adapts the vision language model and is trained solely on unlabeled synthetic data. The resulting PIN, an input agnostic vector, is then added to any image along with the corresponding prompt to enable object localization. Synthetic training data is created by combining background images with synthetically generated objects using stable diffusion, following the XPace paper. Pasting objects onto background images generates a self-supervision signal, which is exploited during training. Multiple objects are pasted to prevent the network from collapsing and only reacting to the most prevalent object in the image. Here example images from our synthetic training data generation. Note that the non-realism is not an issue, since the vision language model remains completely frozen and only the weights of the PIN module are optimized. Additionally, object names not present in our evaluation dataset are used to test the zero-shot capabilities of the adapted model. The structure of vision language models can be summarized as follows. An image is embedded by the vision encoder and then mapped into the LLM space via a fusion network. For Flamingo, this fusion network includes a perceiver resampler and gated cross-attention to integrate the visual information into the LLM. Through this process, the LLM can auto-recursively generate text given a prompt and an image, such as in the image is a monkey. Instead of using real images, we feed our synthetic data into the frozen vision language model. The prompt involves localizing one of the pasted objects in the image. Since the vision language model has not been trained for this task, it is initially unable to output any bounding box information. To enable object localization, we add a positional insert PIN to the vision encoder embeddings, which is element-wise added during the forward pairs of the vision language model. The parameters of the spatial prompt are optimized, which are from the MLP, and the input for the MLP is based on a constant sinusoidal embedding. We use the self-supervision signal from pasting objects to optimize the MLP parameters, resulting in an input agnostic PIN for this specific vision language model. PIN can be viewed as a pathed method, specifically for autoregressive vision language model, and can be implemented only in 10 lines of code. During inference, we just add the constant PIN to any image to unlock the object localization in vision language model. Here is an example of an adapted vision language model based on OpenFlamingo, which can localize objects in various scenarios, including comics, paintings, and normal images. Note that none of the object classes used during pin training were included in these examples, demonstrating that the generic capabilities of vision language models can be successfully transferred to localization. Here are some results on Pascal VOC, where orange shows the prediction of the vision language model and blue the ground truth. The enhanced vision language model is able to localize multiple objects in the image, yet struggles with small objects and cluttered scenes. We first evaluated the in-context abilities of OpenFlamingo and found that even with context, the vision language model was not able to localize any objects, performing on par with random selection. Note, here we use the subset of 3 objects, maximum of 3 objects per image for Pascal VOC and Coco. In contrast, the enhanced vision language model with PIN is able to localize objects, seen by the strong improvement in performance in mean IAU. Moreover, PIN works also better than existing path methods, such as prefix tuning, similar to co-op, visual prompt tuning for the vision encoder and the fusion network, or LoRa applied to the vision encoder. PIN can enable also object localization in other vision language models, such as BLIP2. In addition, with slight modification to the synthetic training data, we can also achieve decent performance on RevCoco. That's it. Thanks for your attention.